Okay, for those who want to follow the slides, they are available on my GitHub as well. They should be available on the Meeting C++ part where the slides are. And if you have any questions, you can easily reach me either on Twitter, where I'm quite active in the C++ community, and via my email, which is positioned here. A little bit of self-advertising. I quit my professorship last year, so I'm now available if you intend to get C++ training or consulting or code reviews. I'm happy to serve you if it fits my schedule. Now, what classes we design and how? First, some of my philosophy that I more or less borrowed or stole from Kevlin Henney is, I think less code equals more software, and there's a lot of value in simplicity. And this also should show in code, and especially my philosophy is don't write code that you don't have to write. And part of this talk is about not writing code that you don't have to write and avoiding code that you might write because you think you need it, where you actually don't need it. In addition, I often strive to look from a high-level perspective to actually be able to get my point across and only show those details that are actually relevant and not building up, let's say, C++ from the ground up, which is just too big to get your head around and understand everything. So I will deliberately leave out parts that you might, yeah, but in my case, I need to. If you have those cases, come to me and I will try to explain to you where you don't need them. Now, one reason to start from one position, start from high level. If you look at what a C++ object is, it's in the standard terminology, a C++ object is, let's say, a value with a location and a type. And if we that's what we model in our classes most often, or in other types. And these things that we model as types and then use as objects very often take different roles. The most prominent role is the role of a value, which is kind of what. And just what's in the value is what makes how the value behaves, how all kind of functions work on it, and what we can do with it. And we will look at what a value, how value can be perceived and what it is on one of the next slides. The second role that an object can actually take is a subject. And for a subject, it's not only the value, it's content that is important, but also where it is. So a subject has a location, and it more or less announces itself by being here. Having a location gives us a lot of properties, especially the next role that we can actually form. We can create a relation to a location of a C++ object. And the relation more or less tells us where something is. And that where gives us additional properties, like, for example, making a subject a polymorphic thing by having a relation to a base class and then hide behind that relation instances of a derived class or of different derived class, and so change the behavior of the system. And then when we consider building classes around these things, there's something very C++ specific what we have to create. All the other things might be created in other languages as well. But in C++ has a unique opportunity to actually create what I call manager types, those that are clean up. Maybe we should call them janitorial types, because they are the ones that silently clean up our messes that we create and do every kind of garbage collection or other cleanup that's required. And that's one of the strengths of C++ that allows us to implement those cleanup types on our own or use them throughout our systems. These might not be all models on a high level that you create, but these are very important one to get your head around and deal with, and not to mix up too much. Now, if you look at the value role of an object, what is a value? We can look far back in the system, and then again, that's a citation I borrowed from Kevlin. A value is an intangible individual that exists outside time and space and is not subject to change. This is from a book by Michael Jackson, which is not the famous pop singer, but one who wrote on structured analysis or domain analysis and other software engineering topics in the past. Now, what does it mean? A value that is just the value. It doesn't have any other, let's say, significant properties, but it's value. So a value is a value. If we look further, we have some other means where Scott Myers told us, when in doubt, do as the ints do, which comes from the saying, when in Rome, do as the Romans do. But nevertheless, ints represent values, and a lot in C++, or most mechanics in C++ stem from the fact that it supports value semantics, which is what we can look at in the following. Now, what does it mean outside time and space? Even though a value can have different representations, it's always the same value. So if we use 42 and enter that as a literal, there are many spellings on how to represent that literal, but the behavior within the program is independent of any of these spellings. It's always the value 42 with the type int. And what's most important is a value object is valid independent of other entities. You cannot invalidate a value object remotely by something else. It just is. And that's very important. You can pass values across to another thread, and because the value's behavior is independent of where it is, the thread behaves by using that value, and it's just there. And that's an important thing. So values just work, and we don't have to care a lot about lifetime and the thing. Values just are. Now, what is value semantics in C++ is closely related, but value semantics is actually the property of a type in C++. The major property is its copyability. So you can have an object of that value semantics type, and you can copy the object, and the copy and the original object have the same value. They behave exactly identical, and the original is unchanged by that copy. So there's you cannot distinguish the original and the copy, and they behave identical, but you can copy, in which is what's actually called value semantics in C++. There's some people argue, oh yeah, it has to conform to a concept called regular, where it's actually default constructible and comparable. But I would say the copyability is the most important aspect of value semantics in C++. And we have even types that have value semantics that aren't values, and we will come to that in a minute. Now, const is somehow an aspect that supports value semantic, or helps with creating stuff with value semantic, because it guarantees that when you copy a const object, it's not mutated, so the original always stays the same, and then the copy only has to make sure that the copied object actually has the same behavior than the original. In addition, we can actually use const to create immutable data structure, which provide value semantics inherently, because you cannot change an immutable thing. That means you don't get into any problems. But this is not the topic of this talk. There's a great talk by Johan Bolivar and his IMA library on how to create immutable data structures and use them in C++. And very beneficial. So we have values and value semantics. What else? The second thing that I refer to were the thing that I call subject. Why didn't I call object? Well, because object has a different meaning in C++ than in most object-oriented languages. So in an object-oriented language like Java, what I call subject here would then be an object. But why it's a subject? Because the identity is the important part. So identity is important. And once we have something with identity in C++, it tends to have a location, and it has a lifetime. So it has, it becomes into, at one point in the program, it starts its lifetime, and there might be another point in the program where its lifetime ends. And that gives some peculiarities, because usually something becomes a subject because I form a relation to it. And that means whenever the subject and the relation's lifetime are somehow coupled, and if the subject lifetime ends, the relation might still be around, and that might mean you have a problem with dangling. And in general, subjects might not be, don't need to be copyable, because instead of copying them around, you form a relation and then refer to it. And being able to form a relation, it allows us to create polymorphic behavior in the classic sense of object-oriented dynamic polymorphism. Now, what else? If we look at the polymorphic subject types, this means we have a base class with virtual member functions, and we create derived classes, and instances of the derived classes can be referred to by a base class relation object. And it to put those objects on a heap requires that the base class defines a virtual destructor, and to not get into problems. There's one let's say, deficit in the standard library. For example, unique pointer doesn't detect if you form a derived to base conversion with the unique pointer types, then there's no check that the base class actually has a virtual destructor, which would be possible but isn't implemented. Actually, when concepts were a thing in C++X, there was a paper not directly proposing, but talking about making unique pointer safe in that way by providing the corresponding concept. But up until now, nobody took the courage to actually change unique pointer in a way, or its default deleter, to get that safeguard in the standard library. A typical thing in a virtual, in a polymorphic base class is that we want to prevent copying. So we don't have value semantics for these polymorphic types, at least not for the base class type. And we want to keep the identity, so there's no copying would lose the identity property, would lose the original subject. And the second goal is to prevent the slicing that might happen when you just take the base class part from a derived class object when you copy it around. And there are other means of dynamic polymorphism that are more modern, or might even be better suited in a value-oriented world, but that's not the topic today. And if you look at relation types, these are types that represent the where of another object, and they have also some interesting properties to think about, especially when you put them into class types. So what is a relation? It's always referring to something else, another subject. So it uses the identity that another subject, another object actually has, and refers to it. And I'd like to introduce you a new German word for those who are not German speaking. A relation object actually enables Fernwirkung, and I will explain that in a second. It's literally translated, it's you could say it translates to remote control or remote influence. Relation objects also enable abstraction with dynamic polymorphism, and it enables the use of non-copyable objects. We already found one category of non-copyable objects, the polymorphic types, but also there are manager types where you don't support or cannot support copying, and those, to refer to those, you actually need to form a relation to them. Now, what does Fernwirkung mean? It's kind of, you can access or modify an object that is not part of the current expression. Everything in C++ that takes hold of objects and then the types is an expression, and usually you have all the relevant objects within an expression. If you write 42 plus 1, it's two value objects, 42 and the 1, and then you have the operation plus, and the result is the result of the addition, 43, again a value, but nothing actually has some Fernwirkung. To actually get a Fernwirkung, the typical thing in C++ is you use references, or the most prominent thing is, for example, you can use a const reference to access a remote object that is actually not directly partaking in the current expression, only the reference to it is partaking in the current expression. We can, and const references are mainly used for preventing copies where they are not needed, where you just want to access the corresponding value. There's another, the L-value references that you can form, and these are for remote side effects. So you can actually change an object that is not taking part of the current expression. So for example, you can have a reference and put the ++ operator on it. And if that's a reference to an int, you're not changing the reference at all, but you change the object referred to by the reference that is actually incremented. And then there's the third form of reference that we can form, the R-value references, and they are mainly used for transfer of ownership, and those are also kind of Fernwirkung on the original object, which might be actually emptied by the transfer of ownership. The same things can happen with other types, mainly pointers, but also with types that have are actually class types, like standard span, like views, like string view, or iterator types, which might be pointers or not, or class types. All these have kind of the ability to provide Fernwirkung to other objects, and the Fernwirkung only works if that what's remote, what's entfernt in German, what's remote is actually there while you use it. And this leads us to a lot of technicalities with relation types. These are the types where things can really go boom or bang or dang, as I said, because they they are potentially dangling. The original object can go out of scope, or it can change, invalidating what you're actually referring to, and this might make your program get undefined behavior. So actually, whenever you use a relation type, you have to put on your superhero cape and track the validity of the relation object and see that it's still valid. The typical safe part is if you use these relation type as function parameters. Some people actually call them function parameter types, especially those that come in a disguise as a class type like views or span. We have the language relation types like reference and pointers, and if you make a class type with a relation member, then that makes your class type also relation type is kind of contagious, unless your class type does specific things about managing the relation. So unless your class type actually becomes a manager. Now, let's look up for the specific C++ things that we can actually form manager types. What's a manager? Whenever you create your own managing type, make sure that you manage just a single resource. If you need to manage multiple resources in a single type, wrap each of them individually in a manager type and then just combine the manager types. Why? Getting things right, especially when acquiring or releasing a resource can actually fail or can produce an error, is really, really tricky to get that right when you have more than one resource. I personally tried that with a unique resource, which I proposed for the standard library, which made it in the standard library fundamentals, but never actually was adopted to the standard library. And because it wasn't adopted, I show you how to create your own manager types, especially a template for your own unique manager in this talk, which allows you to create your own unique managers. And it's not too complicated to actually follow that. Now, what are the different situations? You might want to use a scope manager. An example from the standard library is a scope block, for example, which is not copyable, and it's just for local scopes where you acquire a lock, and whenever you leave the scope, the lock is immediately released. But you might have other situations where you acquire a resource that's not easily duplicable and that you don't need to share, transfer the ownership. You just keep that locally and pass it down with a relation type down the call hierarchy, and then whenever you're done with your function where it's declared, it's cleaned up afterwards. Then the second level are unique managers, where you have a resource that's not duplicable, but where you want or need to transfer the ownership. The classical canonical example from the standard library is the standard unique pointer. And these are also not too hard to DIY, but the most hardest thing to DIY is the general manager for duplicable resources that still require a lot of managing, and we cannot just exploit an existing library type that does the managing for you. And this is where I can give you least guidance, but I tell you how to detect those types and how, let's say, give you a reference frame how to implement them. Now, how do we detect a manager type, or how do you create a manager type? Detecting is whenever a class defines a non-empty, non-default destructor, this means that you actually manage something. The destructor has work to do, and that work means you do some cleanup work. There's a janitor at work that cleans up, or a manager that cleans up, whatever you perspective of manager you have. And that means you usually have a member that is a relation type, and sometimes this relation type comes in a disguise. For example, if you manage a file handle, that is typically represented as an integer, and this is not a pointer or not a reference type, but it still has the relation semantics because it's only valid as long as the corresponding operating system file handle is active and valid and not closed. And this can happen remotely by some other piece of code closing the file handle, and that means your file handle is actually dangling. And so it has the properties of a relation type. And what a manager has to do, it has to care about copying and moving. It doesn't have to support this operation, but it must keep track if it's supported or not. And one guidance, okay, because you distinguish managers from other types by having them a non-empty destructor, never define a destructor with an empty body. You might think, oh, it's not a big deal because the compiler, it would be exactly behave the same as the compiler would do it. Yes, but that's code that you don't need to write. So why did you wrote it? So everybody reviewing your code has to think about, oh, was there something there that got deleted in maintenance, or was it a placeholder and something wasn't and that is missing? And why is there an empty destructor with an empty body? Don't do that. And the new upcoming MISRA guidelines will actually have a rule that corresponds to that. And there might be some exceptional cases where you're not managing a resource by an invariant that is non-local, but perceiving how you squeeze your eyes, you're actually managing a resource, and therefore I'm not going into detail more about those types. I usually see them in code examples explaining all kinds of stuff about move and copy that can go wrong, and you don't want to write code where move or copies goes wrong. Now, technically, you look at the, I already told you that if you have a scope manager that puts things in a box and cleans up, it's non-copyable, non-movable. Technically in C++17 on, because of copy elision, you might even be able to return it from a function when copy elision takes place. Then there are the unique managers where you have the transfer of ownership happening. There's, which means you have to care about what happens when the resource was transferred. So the unique manager has to have a deliberate empty state when it's moved from. And then there's a general manager where copyability is a key issue, and you might actually only implement, or you only need to implement move operations when the copying is quite expensive and you want to have move as an optimization, which is the second usage of move operations. Now, why do I want you to think about these class categories and types? It's to have a mental model about the things that you create. Is makes it much easier to argue what you actually want to create and how to create it on a technical. And once you consider you build things together from other parts, you knowing what role the other parts play also helps you to get you the influence. And it also helps you with code review or reading code. If you see something, a local variable of type string view, for example, that should trigger you, oh, it's not a parameter type now. We have something hanging around here. Is it valid? So you have to trace the origin of the string view, where the origin object it refers to, its subject it relates to, and figure out if it's valid. So that's kind of a thought model you should trigger immediately when you use things like that. And defining classes correctly can actually be overwhelming. There are books around with 200 plus pages just talking about move semantics and what you need to do about with the special member functions and how to use them properly. And I think you shouldn't know all the details of these 200 plus pages to write a valid, a useful class type. And the thing is, with C++11, we now have 5 special member functions we always need to consider, according to some sources, if we want to write a class correctly. We have a destructor, and we have a... Let me see if I can check my... So we have a destructor, we have the copy constructor, we have the copy assignment operator, and I want to point out to you that I actually started to define my copy assignment operators for general managers, where I have to define them with an ampersand to make them L-volley qualified, so they only apply to an L value on the left-hand side, which is how they should be defined, but the language has the default wrong here in that case for legacy reason. And then we have the move operations as well, and again we see the move assignment operator actually employs the L-value ref qualification to get there. Important thing, if you define move operations, make sure when you need to define them that you make them no except, otherwise they wouldn't be used for optimization in case of a general manager, or you might actually lose your resource when you use them in for transfer of ownership. So the only useful move operations have are actually qualified with no except. In theory, you have to think about the 3 things: public, protected, private, to understand if they are actually, you could make each of those public, protected, private. Usually you will make things public that are used and not on the protected or private part, but in theory you can define all of them in each of these categories. And then each of the 5 special member functions can either be not declared at all, declared as defined as equals default, defined as equals delete, or with a non-empty body. And these are things to get your head around. If you do a simple computation, you get about 50 possible ways on how to define your classes. Most of them are ridiculous, but in theory, a novice might not be able to actually figure out which are the good things. And then you all have the different spellings that are still considered valid move or copy operations by the standard. And this is not a place where you actually want to go. And if you look at the table of Howard Hinnants, which he presented at ACCU 2014, you see all the different rules the standard has. If you define one of the special member functions, what happens with the other special member functions if you don't say anything about them. And it even shows the deprecated part where you get copy operations when you define one of the copy operations or destructor, which is considered to be wrong by the standard, but cannot be changed because it has been that way ever. And this is actually the area where Scott Meyer's rule of 3 came from. But knowing that table by heart and considering whenever you define a class is really overwhelming, and that's not what you want to actually do. Now, just consider it's not only which special member functions you define, but also the influence of your sub-object, either as a base class or as a member variable that you have. The good thing is whenever you have a value, everything is just fine. You can easily combine values. All the defaults just work. You don't have to talk about the special member functions because the compiler provided ones are just okay. If you have a relation type as a member of your class, like a pointer or whatever, then it becomes contagious. So your class becomes a relation type, like for example, span employs a pointer to refer to the area that it relates to, and that makes span a relation type because it doesn't have any additional managing capabilities. On the other hand, if you look at unique pointer is a unique manager. Even though it contains a pointer type as a member, it's no longer a relation type because it's managed. It is a unique manager type. If you look at polymorphic base types, if they are defined properly, they shouldn't make any problems with slicing or heap allocation. But again, if you don't do them well, you can get all kinds of problems. Now, if you look at the scoped or unique managers, each of those are contagious as well. If you have a member or base class that's non-copyable, your class becomes non-copyable, which might be a desirable thing. Otherwise, you have to do things around like manage things again. And this is where whenever you get up to the general manager, which is copying and has value semantics again, you're back to step one, where the original values are just fine. Now, let's get to the beef, how you actually define those types. Now, how do we define a class? The best thing is don't declare special members, and this is what the rule of zero is about. And there's some exceptions where you must, and I will tell you more about the exceptions because rule of zero is easy. Just don't declare any of the special member functions. If you look at the core guidelines, they have quite a weak motivation. It says, okay, it's simple and gives the cleanest semantics. Simplicity is very good as a motivating factor, but this is where the core guidelines could actually be improved. And why? What I say with the rule of zero, implement your class in a way that the compiler provided default implementations just work. And even if you say, oh, I know what the compiler would do, and I just declare my special member function and define them with equals default and delete, just like the compiler would do, don't. Because you might lose triviality or the aggregate ability of your class, and you might actually change the behavior in subtle ways, even with equals default, that are not obvious by that, because you might change the overload set or have some other things that might happen. There's two exceptions for equals default. One is to resurrect the default constructor when you have to define another constructor, and the other one is to actually define the virtual destructor of a polymorphic base class where you have to define it, otherwise it won't be virtual, and that's one of the defaults C++ got wrong. Now, when is the rule of zero not well suited? Whenever your class needs to define a destructor. And this was most of the time the case in Scott Meyer's rule of three, and it's in most cases still for the non-rule of three. And I skip over some kind of exceptional cases that I usually only find in kind of explanation code that's not real world code, or in buggy code that shouldn't be written at all. Now, for the polymorphic base class, we can refer to the core guidelines who told us, okay, make it public and virtual, and you should prevent slices in that cases. And so a polymorphic base class should suppress copy and move operations. And again, there are some school of thoughts how to prevent copying. There are the old options in C++03 or 98, where you have the private copy operations. That's no longer necessary. You inherit from non-copyability, like boost non-copyable, which is a bit less subtle, telling you, okay, I don't intend you to copy that class. And in C++11, people are proposing, okay, just delete the copy operations. The problem is you delete the copy constructor, and you have to delete that. It doesn't go away automatically when you just delete the copy assignment. That requires you to resurrect the default constructor. So to get rid of copy, you have to actually define 3 special member functions, which is kind of a lot, and my opinion is it can be done simpler. So less code to write, more software you get. How do we do that simpler? Well, we look very closely at the table, and if you follow Howard Hinnants' talk, it takes a long time to get the last line. And the last line, if you look at, okay, if we actually define a move assignment, even if we define it as equals delete, we will end up with a situation where we don't get a move constructor and where the copy operations are deleted automatically. So they're not compiler provided. So we get rid of the copy operations, no move at all, and the destructor is still there, and especially the default constructor is still there because we didn't have to define a specific constructor. And this is what I call the rule of Desdemona, and like Desdemona, it's just if you define a destructor for a polymorphic base class or for a scope manager, delete the move assignment, and you get rid of the copyability, which is a desirable feature in that situation. Now, for a polymorphic base class, in my opinion, we go there, we will have a virtual destructor because we have some other virtual member function, and there's a single additional special member function we need to care about, which is the move assignment operator that we just define as equals delete, and it is a perfectly fine polymorphic base class that is not copyable and just works. And if you can find a simpler way of doing that correctly, please tell me, because I am happy to make this even simpler. Now, managers. These are the most specific C++ thing that you can actually create them, and there's really a good stuff to work about, and they employ the ability that C++ has deterministic object lifetime and the destructors. So we have the thing called resource acquisition is initialization, or scope-based resource management, and that's where the manager types are important. Most of the time, you would just rely on the manager types provided to you by the standard library, like the standard containers or standard string, or if you want heap allocation, like unique pointer. But you want to, if you really want to do it yourself, you might end up writing your own managers. And the principle is the constructor acquires a resource, the destructor releases a resource, and you need to take care about copying and moving. And this is actually the reference to the unique resource, where I provide a generic solution for that, which I believe is too error prone to actually standardize. It's better to DIY for your own kinds of resources, and the standard doesn't provide one for you. And again, manage a single resource, and we've seen that slide already. So let's jump into the details how to actually create our manager types. The simplest one is the scope manager, and we will have a constructor that acquires the resource. This typically will come with parameters to actually identify the resource to be acquired, and we will have a destructor that releases the resource, and it will have a body doing the actual work. And because it's non-copyable type, we will apply the rule of Desdemona by deleting the move assignment operation and get rid of all support for copy or move operations. And we will have some relation type that denotes the resource that is actually managed. And this is as far as it goes. Anything beyond that is very specific to the kind of resource that you actually manage and how you manage that. And this is what you have to do as your homework to create a scope manager. Now, a unique manager gets more involved because you want to support transfer of ownership. That means that a unique manager either holds a resource or might be in a state where it doesn't hold a resource, and the destructor might distinguish these two situations or needs to distinguish these two situations. So the cleanup must only occur when the unique manager does hold an actual resource. Otherwise, you might actually release a resource twice, and in case of memory, this undefined behavior. In case of other resources, it might get you in the situation where you either have a dangling use of the resource, or a double free or double release of a resource that is undesirable. Now, how do we get there? Because the unique manager has to have that extra piece of state. For pointers, it's easier. Unique pointer just uses a null pointer to denote the release state, but for other resource types, you might not have the extra valid value in the type to denote the released resource. That's where I suggest, okay, start out with the standard optional of the resource type to denote, okay, when the optional is empty, then you don't hold the resource, and then the destructor of the unique manager doesn't have to do anything about cleanup. And it also allows us to give us a very, let's say, schematic implementation sketch or a template for the move operations that you actually require to have. You will also have typically for a unique manager, a default constructor that just can be defaulted, because default constructed optional will have an empty, will be empty, and that's the state that it corresponds to the moved from state of a unique manager. Now, if we look at we'll have a constructor that actually acquires the resource to get there, and we will have a destructor that does a cleanup, and we will have to define the move operations, move assignment, and move construction. And you see we have from our 5 special member functions, 3 of them we actually have to define. By defining the move operations, we don't get any copy operation support, which is what we actually want to. And this is a kind of a new rule of 3 for move-only types, where you have defined the destructor and the move assignment and move construction. Now, how do we implement these operations? Let's glimpse into that. And first, I'd like to point out, this is my one-line explanation how move actually works. You have on the right-hand side a box with a letter in it, and the actual move assignment or move construction of the left-hand side transfers the letter to the left-hand side and potentially makes the right-hand side empty. And if you have a transfer of ownership that actually happens, the right-hand side is empty. But note, a copy operation is always a valid move operation if the type supports copying. So you actually might duplicate what's in the box and have it at both sides, but that's only for general manager where this is supported. For a unique manager, you actually have to transfer the resource from one side to the other. Now, how do we do that? For a move constructor, there's nothing on the left-hand side, so it's kind of nothing there. We construct the optional by moving the others optional around, but that doesn't necessarily empty the optional. If the held resource type is just copying and the other option is not empty, we will get a copy of the resource handle, like a pointer or the integer for a file handle. So we actually have to make sure that the other object doesn't clean up in its destructor. So we actually reset the optional on the right-hand side to make sure that it will not clean up the resource and that the current constructed object holds onto the resource afterwards. A similar thing has to happen on the assignment operator. The problem is with the assignment, we don't want to lose the resource when you clean up the left-hand side and transferring it to the right-hand side. There are some people who say, oh, we should just don't care. I think it's better to have a deliberate move from state when you define a move-only type, and the deliberate move from state should be empty. And therefore, we do this check about, are we doing a self-assignment? If not, we actually release the current left-hand side and then swap left and right-hand side, so the right-hand side is empty afterwards. And if you look at the release operation actually checks if the optional is empty. If not, you have to write your own code here to really release the resource, which is resource specific, so I cannot give you a template for that. But then afterwards, we actually reset the optional and then you will end up and clear the optional, so this object is actually empty. And this is also what you will actually call from the destructor, and that is how you implement your unique manager. And the only line that is very specific is how to actually release the resource here and how to actually implement the constructor acquiring the resource, like you had with the scope manager. Now, what else? For a general manager, things get more complicated and more tricky because duplicating the resource is depends heavily on the resource, what that actually semantically means. If it's supported for memory resources like stat vector or stat string manage, duplication means you duplicate the contents of the memory and the memory region. And this is just what happens in there. And if you have a resource where that duplication is expensive, it might actually might make sense to additionally support specific move operations to optimize them. But that's not a prerequisite to become to get value semantics, and it's only necessary to think about those if the copying happens frequently and is actually expensive. And again, for a general manager, especially if you provide move-only operations, it might make sense to have a default constructor to create a kind of an empty thing that is corresponds to the move from state, but a little bit like the move operation is not actually required to get there. And if we look at that, we get here, if you just support the destructor and the copy operations, we end up with Scott-Meyer's rule of 3, the classic one, or some people would say, oh, it's a rule of 5 or 6 because I have to talk about and implement all of these special member functions that we have to care about. So we provide value semantics for a resource that doesn't give us value semantics, and it only makes sense when the resource is duplicable, and it usually requires expert level coding, and whenever you can get around without implementing your own general managers, go there and reuse the existing ones in the standard library. And again, the resource must be actually copyable or replicable to get reasonable value semantics. Now, getting to our takeaway, what actually will we get there from my talk about the role models of our C++ object? Whenever you create types that are not just value types, that just don't work out of the box, use them with consideration. Deviate from value semantics only when needed. Sometimes it's required for polymorphic bases. There are talks about how to get polymorphic behavior without relying on relation types directly in user code and still having value semantics, most prominent by Sean Parent. I had some feeble attempts on that as well. So you might find talks on YouTube by me on how to implement polymorphism without just using virtual in your code bases directly. There are other situations, scoped and unique managers, where it's viable to deviate from value semantics, either because copying the stuff is very expensive and you want to prevent that, or because you don't need the value semantics at all, because things will live somewhere, and the lifetime of the scope where they live is just sufficient to support everything. Whenever you have relation objects in your code base, either in this as reference or pointer types, or in disguise as class types, handle them with care. Put on your, let's say, goggles that figure out lifetime and figure out if the lifetime is managed well. They're usually very safe to use as function parameter types, and very error prone if you use them somewhere else, especially as return types. And this is something to watch out for, especially if you go into a code base where you see pointers throughout, especially as members. Watch out that you don't have just a non-managing type that is tricky to use. And when we take about special members, it doesn't have to be an art and doesn't require hundreds of pages to get your head around. Just remember the rule of zero rules, and it's often good enough and sometimes even the most optimal way of dealing with code. And remember, premature optimization is the root of all evil. And I think some people claim, oh no, you should take care, but don't optimize what you cannot measure and what you haven't measured before. And again, take away, take at home, never define a destructor with an empty body. If you have code bases doing so, just delete them and get rid of that crafty code. And equals default the virtual destructor in the base class, and then apply the rule of zero in the derived classes if you prevented copy operation in the base class. If you want to make your derived classes manager types and use them individually somewhere, that's in principle okay. Just make sure then that you are able to define those operations correctly, which might mean that you not apply the rule of Desdemoova in those cases, but this is really very specific and it's rare to have to do so, and there might be other means to get there. And again, remember the three kinds of managers: scope-based resource management, key to C++ success, especially in contrast to C. And think about the rule of Desdemoova for scope managers, the rule of 3 for move-only types, which are unique managers, and the classical rule of 3 or the rule of 5 or 6 for the general managers. If you really need to go there and better get help, it's like you're really going to the rocket science part of C++ to get that right, especially if you want to write them generically. And there might be people around at conferences that know how to do that, but it's not the common off-the-shelf C++ programmer who knows how to do that safely. And what was missing from this talk, running into the end, well, I didn't tell you a lot about how to cope with the relation object. That's part of an extended talk or a different talk. And that's where you have to put on your protective gear and your scrutiny and analysis and your fire extinguisher or smoke detectors to get rid of potential dangs and make sure that they don't go bang, and that's possible. The other thing is, I didn't tell you how to encapsulate virtual, like getting value semantics by using std variant, for example, or encapsulate them with the envelope letter pattern, like Sean Parent can show you in one of his talks. And I think I'm done right now, and I hope actually somebody listened to that and watched the video or online. And again, you can access the slides, and I'm happy to get contacted with questions or critique on that, because I want to learn and not only teach, so kind of improve my learning. And so far I haven't seen any questions in the chat, but it might be that everything is so clear or that nobody actually listened, and I hope somebody will actually listen to that and learn something from that.
Well, thank you, Peter. That was a nice talk. I listened, and I know that the others have listened. So if you want to speak with Peter about this, you can see him in the launch. And I'm going to take us now offline, as there seem not to be any.
Jens, one quick question. Which room in the lounge should I actually head to? Because I'm kind of extra now.
Yes, the big table.
Okay, I'll be showing up at the big table in a minute or two when I switched back to Hubilo on my system. Okay.
You also need some time. So you can meet Peter in the big table in the lounge. And until then, I wish you a happy conference. And